develop a smart factory and moving ahead with the sustainable and smart way of designing and developing products. And additive manufacturing is one of the key technology facilitating smart manufacturing. And certainly, a lot of research is progressing in terms of enhancing the capabilities of additive manufacturing systems from several perspectives. And a lot of challenges from industrial viewpoint are also have given a long way for us to take ahead with very meticulous research in terms of developing core technologies as a part of it. And also some of the recent advancements in additive manufacturing which need emphasis and focus include 4-dimensional printing, where from 3-dimensional printing we are moving ahead with 4-dimensional printing, with the ultimate focus on important research agenda as design for manufacturing and assembly, we call as DFMA. In line with that, here we in additive manufacturing called DFAM, designing for additive manufacturing, where we explore several include like topology optimization, shape optimization, and so on, which are very, very essential and lattice structures development, because of the objectives for develop products to be of lightweight structures, and such optimized structures are very, very essential for enhancing product performance. And we could very well understand the developments happening in varied industrial sectors, starting from automotive, aerospace, defense components manufacturing, and maybe like medical applications, and a lot more diversified applications are prevailing for additive manufacturing. And one of the unique aspects of additive manufacturing is it's a very good example for the research which is interdisciplinary in nature, because it involves engineers from several disciplines and researchers from several disciplines working together in order to develop a comprehensive system integrated with the technologies. And certainly this FDP will have and will contribute in this pathway towards developing robust additive manufacturing technologies. And the experts who will be delivering this lecture in the 2-day FDP will help the participants to understand some of the theoretical concepts. I wish the organizers of this FDP and great success in taking ahead with the set outcomes of the FDP. With this note, I would like to conclude my inaugural note, and let me further discuss in my session as a part of it. Okay, thank you all.
Thank you, sir.
Thank you for your kind words.
Actually,
Program. Really, you are a great inspiration for us. Really, you're motivating, ma'am. Thank you so much, ma'am. I extend my gratitude to our guest of honor, Dr. Vinod sir, who has rendered a valuable time for this program. Thank you, sir. I also extend my thanks to the other eminent professors who are speakers from various premier institutions who are going to join with us for the next 7 sessions. Thank you all. I also thank my coordinators, Dr. Veerapan sir, Dr. Gopinath sir, and Dr. Manigandan sir for their sincere and dedicated work towards this program. I thank, actually, the program should have participants. Really, I thank all the online participants who are going to join in upcoming sessions. Really, thank you so much. I thank my faculty members who are present here. I also thank my student volunteers, and special mention to Prithviraj from 3rd year, who designed the first brochure for us. Thank you, Prithviraj, and also my editor. Thank you so much.
Thank you for sharing your love and support. Now I request everyone to rise for the national anthem.
Please start national anthem.
नायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल उच्चल तरंगा तब शुभ नामे जाहे तब शुभ आशीष माहे जाहे तब से दाता जन मंगलदायक जय हे भारत भाग्य विधाता जय 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 हे
Thank you.
Great.
Department in National Institute of Technology, which he completed his bachelor's degree in mechanical engineering from Government College of Technology, Coimbatore, and master's degree in Python production engineering from PhD College of Technology, Coimbatore, with a PhD. He was a top ranker in his undergraduate and postgraduate studies. He has been awarded National Doctorate Fellowships for pursuing research by AICTE, New Delhi. He has been awarded Outstanding Paper Awards by Emerald Publishers, UK, for the year 2009 and 2008. He received Innovative Student Project Award in the year 2010 based on his PhD. Thesis from the Indian National Academy of Engineering, New Delhi. He is a recipient of Institution of Engineers Young Engineer Award for the year 2013-14. He has published over 150 papers in international journals. He investigated 3 sponsored projects funded by DSP and CSIR. He is on the editorial review board of various international journals in the specialization of manufacturing and industrial engineering. We request you the honor of your presence, sir. The session will start soon.
Thanks for the introduction. Let me share my content. I hope my content is visible. Is my content visible?
Yes, sir.
Okay, I hope my voice is audible. Am I audible to all?
Yes, sir.
Okay, so any my network is perfect, but still any network interruption, kindly alert me. Okay, fine. With this, I shall proceed with my session. I'm Dr. Vinod, working as professor in the Department of Production Engineering, National Institute of Technology, Tiruchirappalli, and I'm coordinating the rapid prototyping lab for our department. And the topic of my session is on additive manufacturing and Industry 4.0. So I'll be proceeding to the next overview slide. Is my slide visible? I'm into the second slide. Is my slide visible? I hope you all could see the second slide. Yes?
Yes, sir.
Right. Okay. So my session is threefold. First, I'll be discussing about additive manufacturing. The second part will be on sustainable manufacturing and its insights for additive manufacturing. And the third part of my lecture is about Industry 4.0. So let me try my best to discuss about these concepts within the scheduled time. And as I mentioned, additive manufacturing emerged in the term rapid prototyping initially, where the objective was to support prototyping phase of product development. As being shown, once we generate the design concepts, we progress with the further analysis and optimization. Then we went ahead with the development of prototypes. Initially, in the absence of rapid prototyping, the prototyping activity consumed more time, and the products could not be brought to the market within the stipulated time, and hence the need for rapid prototyping had been thought about. And rapid prototyping is a layered manufacturing approach where we try to add material layer by layer and we try to end up with the final product.
Sir,
That's the idea. Yes. Yeah.
can you put in the slideshow, sir?
Yeah. Normally in the Google Meet, when we go to the full screen mode, that is that slideshow mode, there will be difficulty. I will try, but still, if
Okay.
not, we will revert back. Now I have put in the
Okay, sir.
slideshow. Is it fine?
Sir, it's fine. You can go ahead, sir.
Yeah, then it's fine. Okay. So this layered manufacturing technology had been brought with the objective of prototyping activity. Then later it had been expanded for further tool making and actual manufacturing of end-use parts. Now I am in the fourth slide, time compression engineering. Could you all see?
Yes, sir.
Right, fine. So in engineering approaches, we have two methods. One is called sequential engineering and another one is called concurrent engineering. In sequential engineering, one activity next, bring the products the right time to the market. That's the objective of concurrent engineering, and rapid prototyping is a very obvious example which can support this prototyping, tool making, and manufacturing activities concurrently as a part of it, and that's how it helps of the developments and dealing with the challenges. This is the basic scheme of rapid prototyping.
Sir,
We have about yeah, that's what I
changing,
told
sir.
in Google Meet. Always this issue is there. That's why I kept in that thing. I'll just share again.
Okay.
I have zoomed and I have kept. Are you able to visualize this slide?
Yes, sir. Now the fifth slide is visible.
Yeah, full slide. That's why I mentioned if you go to that slideshow option, there are some difficulties in the Google Meet platform. That's why I have zoomed and I have kept to the maximum possible viewability. Right. Fine. So in the basic scheme of rapid prototyping, we have three phases. One is pre-processing, second processing, and post-processing. In pre-processing, we are concerned with developing the numerical design, that is nothing but either a surface model or solid model, and we try to generate an STL file. As we are all familiar, STL file is the file format which any rapid prototyping or additive system can understand. Then we try to build the supports. It is necessary based on the geometry of the part. Then we slice the model layer by layer. We develop prototype. We go for any secondary processing activity like we do in powder metallurgy, maybe like any sintering or oven curing or infiltration, any kind of a secondary processing activity to enhance the engineering properties of the product. We try to do it. This is the basic scheme of rapid prototyping. So this slide shows the classification of rapid prototyping technologies. We have several technologies. In this lecture session, I'll be focusing on three primary technologies of additive manufacturing, like fused deposition modeling, stereolithography process, then selective laser sintering. I'll be able to explain that why I have selected those three technologies as a part of my discussion. This is the first process we will be discussing, fused deposition modeling. Here the raw material is in the spool form, in the wire form. So we have both model material and support material. They are being fed to the melting chamber where we have heaters through which we'll be able to heat the polymer, that raw material spool, and the molten polymer will be passed through the nozzles. It will get deposited layer by layer as a part of it. Once a particular layer is completed, then the platform will be lowered. Then the raw material spool will be fed and the molten polymer will be passed through the nozzles. It get deposited layer by layer. And also we have the concept of support structures. For overhang parts of our intricate structures, we try to provide support structures. Both model and support material will be the same type of raw material. Maybe if it is an ABS, both will be ABS polymer and so on. This fused deposition modeling process it's a non-laser based process. In additive manufacturing, we have one classification is whether a system employs a laser or not. It's a non-laser based process. And here the concept of support structures is there. That's again a classification, whether it deploys a support structure or not. Next, this fused deposition modeling is also called fused filament fabrication, and it is widely used in 3D printers. The reason being, it's a non-laser based process, and it can support the systems, and there were no laser optics being involved. The system is cost effective. That's the reason it was widely used in 3D printers as a part of it. And as per ISO standard, this fused deposition modeling is called material extrusion type additive manufacturing, because here we are extruding the raw material and accordingly we are forming the structures as a part of it. So it has several advantages. As I mentioned, it is more cost effective and so on as a part of it, and it has applications in several domains, starting from design, visualization, functional testing, and so on as a part. This is about fused deposition modeling, and this technology, as I mentioned, it had been widely used in 3D printers as a part of it. Mostly the focus was to make polymer based parts. That was the focus of fused deposition modeling. The next technology is stereolithography process, SLA. Actually, this technology originated first, and it marked the evolution of rapid prototyping systems. That's why even the STL file we call by the term stereolithography file. If you see here in the system, raw material will be in resin form, liquid resin form. The raw material will be taken in a resin tank, and accordingly the laser will be passed through the laser optics. Type of laser being used here is UV laser, and once the laser is being passed, it will heat the laser will be passed to the resin tank, and so once a particular layer is being exposed, it will cure the resin according to the profile of the part. Where all the part to be created, then it will cure the resin. The laser will cure the resin in that place. It is also called laser writing, where the laser is used to cure the polymer resin based on the profile of the part. Once a particular layer is being over, then the platform will be lowered, then the next layer of resin will be exposed, and the laser will be passed. It is used to cure the resin. It goes by a point-by-point route, and then it creates a layer as a part of it. This is about the stereolithography process. As per ISO standard, this process is widely used for several industrial applications. As per ISO standard, it is called photopolymerization process, VAT photopolymerization, polymerization-based additive manufacturing process. And the advantage of stereolithography process is, here there is no concept of support structures, and it has very good dimensional accuracy as a part of it, very good resolution it creates as a part. That's the reason the stereolithography had been explored for precise fabrication in terms of micro and nano level fabrication. And one of the variant of stereolithography is called micro SLA, micro stereolithography. It's a part of it. The reason being, SLA process has very good dimensional accuracy. In micro SLA, if you see the laser beam will be focused to a spot size of about 1 to 2 micrometer, and maybe like it creates thin layers of the order of 1 to 10 micrometer. Whereas in a traditional stereolithography process, SLA process, if you see, the laser spot size and the layer thickness will be of the order of 100 micrometer range. And that's the reason stereolithography had been explored for this kind of precise fabrication when compared with other technologies. So this micro SLA is one of the variants of SLA which has been used for precise fabrication, maybe in terms of automotive, defense applications, and so on. Another variant of SLA is called digital light processing. We call by the term DLP process. DLP process is it's a derivative of SLA process. The idea will be, here instead of a laser, we'll be using a projector light source to cure the resin. That's one of the difference. And second, as I mentioned in SLA process, we go by point approach and creates a layer. Whereas here in digital light processing, we go we try to create a layer at a single stretch. We don't go by a point rule, but it will be the layer formation will happen at a single stretch as a part of it. That's the differences between DLP process and SLA, but it's a derivative of SLA process. As I mentioned, these technologies, micro SLA and DLP, have variety of applications and prototyping, and maybe like functional testing, jewelry, parts manufacturing, medical applications, and automotive, aerospace components, and so on. So till now, we discussed about two technologies. First one is FDM process, fusion deposition modeling, and the second one is stereolithography process. And in stereolithography process, we discussed about two of its variants. One is micro SLA, and second is about DLP, digital light process. The third technology for discussion is selective laser sintering, SLS process, where the raw material is in the form of a powder form. You can see in the scheme, the principal scheme which is being depicted, there are two powder feed cartridges which can feed the powder to the deposition chamber, and there will be a roller which will spread the powder uniformly across the deposition chamber. Then the laser will be passed, and the laser is used to heat the powder bed to a temperature which is just sufficient to fuse the powder. Here we are doing only fusion, not melting. Once a particular layer is over, again the powder feed cartridges will feed the powder, and the laser, the type of laser being used here is CO2 laser, and the laser will heat the powder bed to a temperature which is just sufficient to fuse the parts. And according to the profile of the STL file, this pure heating action will happen, this fusion will happen. And this SLS process has several industrial applications, and as per ISO standard is called powder bed fusion process. And it has its own variants. As we have seen in SLA, we have a direct metal laser sintering, where in SLS mostly it had been designed initially to take care of only polymer applications. Next, in DMLS, the metal alloy powders made of metal alloys are being deployed. Then we have another technology, an advanced technology called SLM, selective laser melting, which is having capability to fabricate metal parts as part of it. So there in SLM, the difference between SLS and SLM is, in SLM, we go to the actual melting range and we try to form a homogeneous structures. But we'll be deploying a high power laser. So using the high power laser, we'll be able to go to the actual melting range, and then we go for melting, and we try to form homogeneous structures of metallic parts, maybe like made of titanium and other metals in line with the industrial applications. So in SLS, we have two variants. One is DMLS and another one is SLM as a part. So these are the three technologies, basic technologies of additive manufacturing, starting from FDM, then SLA and SLS we discussed. Next, we will proceed with the trends of 3D printing. Okay. So as we all know, the 3D printer is an upgraded version of 2D printer. In a 2D printer, it try to print the text on a sheet of paper on a 2D medium, whereas in 3D printer we print the object in 3 dimensions. That's the difference as a part of it. And if we go through the trends of 3D printing, before I proceed with the trends of 3D printing, any queries from the faculty members, scholars, or students, you can post in the chat box. Maybe interimly, I can see some queries, or towards the end of the session, I'll be able to discuss on the queries. Any queries, feel free to post in the chat box. Okay, so as we see the evolution of this additive manufacturing and 3D printers, somewhere in 1980s, we could see the idea of 3D printer initially being developed, the Charles Hull model of a 3D printer. We could see the hardware and the software and the kind of the workstation systems used in those days, and how difficult during those days, that is in the absence of CAD platform, where they may have to depend on different basic systems in order to develop a 3D printer. Now, if you see maybe like in the next across the evolution, somewhere in 1990s, the Stratasys have brought the idea of the fused deposition modeling based printers, and very well we could see the kind of a CAD environment that is being shown, the CAD platform and the interfacing hardware as a part. And they developed the idea of FDM based 3D printers. Then in 2005, we had the idea of open source printers. They are called RepRap machines. That means self-replicating type machines. A 3D printer can print few of its parts. But ultimately, the idea was that they have to develop a 3D printer from another 3D printer. That's the idea. So initially, a 3D printer can print few of its parts. That was the idea. And the same time frame, you could see SLS technology had been brought in order to facilitate laser-based additive manufacturing of products, with the raw material being in the powder form. Next, if you see around 2008, the replicating printer, as I mentioned, RepRap machine, the capability was enhanced, and we could see a 3D printer can print almost majority of its components, and it can give rise to another 3D printer. That was the idea. And the same timeline, if you could see a 3D printer, which is used for some concrete printing, which was developed in Loughborough University, UK, where the 3D printer has a kind of a gantry robot arm. It can deposit this concrete floor for commercial applications, construction type applications. And if you could see that in the scenario, present scenario, the 3D printers are being used for construction type applications as well, where the precise deposition of the material is also significantly essential. Then in the same timeline around 2009, we could see the 3D printers used for some personal applications like household applications, where we can see the kids, they want to print the toys of their choice. They use 3D printer. They pick the CAD file of their choice, maybe like a digital file of their choice, and they try to print the toys of their choice. But it's a very excellent example for the personalization, where the products are being requirements of the customers. In 2011, we could see 3D printers being used in food industry, especially in the pizza shops. We could see the kind of this precise deposition of the food flour is very essential, and we could see the 3D printers being used. And the idea was developed from Cornell University to support this kind of 3D printing applications in food industry. Fine. As we have seen among the 3D printing technologies, the VAT photopolymerization, SLA, and powder bed fusion, SLS, metal extrusion, FDM, they are very essential and basic technologies. And that is the reason in my presentation, I focused on these three technologies as a part of it. And apart from that, we do have binder jetting, where it can support like parts printers. And in this slide, you can see the technologies widely used in 3D printing. If you see the share of FDM, it's around 64%, followed by SLA cum DLP around 18%, then SLS around 11%. Now you'll be able to see the justification that why I selected these three basic technologies for my discussion: FDM, SLA, and SLS. They are widely used as a part of it. Coming to the materials used in 3D printers, PLA and ABS, they have the significant share, and also followed by PA and other polymers as well. And as I mentioned, initially the machines could support only a single material, but now the capability had been enhanced. In a printer, we can process maybe like 2-3 materials as well. The conditions of the architecture and the conditions of the machinery, the system, equipments are being designed in such a way that it can take care of a class of materials with a certain properties being designed to process them. And as we could see, the 3D printing applications in diversified domains, starting from automotive, moving ahead with aerospace, defense components, food industry, and so on, as a part of it. So now we completed the trends of 3D printing. maybe from materials perspective. And here, initially when we started with the project, we had a constraint because the pump design is slightly complex and it involves several numerical computations by analyzing the characteristic curves and so on. So once we specify the head and discharge, and accordingly all the parameters, design parameters have to be computed by analyzing the characteristic curves. When we started doing this task manually, it was time consuming and it involved more computations as a part of it. Then to overcome the constraint, we thought of a kind of a support system which can facilitate this computation as a part of it. Wherein by specifying the head and discharge through the support system, the characteristic curves will be analyzed, the specific speed will be computed, and accordingly the design parameters for the impeller and casing will be computed through this support system. A part of it have to be made in line with the computed design parameter, consume time. A part of it. Then we thought of developing or utilizing the parametric design approach in CAD, where we know the significance of parametric design is once I set a base design, I define a chain of parameters. Accordingly, the dimensions will be computed as a part of it, and I can develop different designs. These are some of the one on the bottom is a derivative design which we made. Likewise, we made some and we performed some analysis, a CFD based analysis we did, and we obtained the velocity contour and we analyzed, and accordingly we could develop the prototype, for which we went ahead with the FDM process, and using this FDM Maxim machine, we fabricated the prototype. The one on the top is an STL file of an impeller, and the one on the bottom is the fabricated impeller part. But in this case, in this project, we fabricated the impeller using ABS, but the actual material is something like a bronze alloy. Then we went ahead with the secondary process like infiltration, and we could infiltrate that bronze alloy powder, and that way we could enhance the engineering properties in line with the industrial developments. And we had an experimental test rig in the company, and accordingly we could test the fabricated prototype, and next it had been taken ahead with the actual implementation. This is one of the study where we utilized an FDM technology for fabrication. And this is the 3D printer we have in our lab, but in our printer we have 8x6x16. And another important parameter is the layer thickness. It's concerned with the dimensional accuracy. And other parameters like size and weight, power requirements are some of the traditional parameters we consider. And this is the software. Initially we had like the Catalyst, next we had been upgraded to GrabCAD. And the purpose of this software module is that it facilitates all the digital analysis prior to the actual fabrication. Once we import the STL file, then automatically the support structures will be fabricated depending on the geometry of the part. All the software modules, they have their capabilities to generate the support structures in line with the profile of the or the geometry of the part. And accordingly, we can do certain optimization during design phase in terms of the support structures in line with the applications and so on. Right? And this is again a kind of a automotive mirror we have fabricated as a part of one of the typical projects. Okay. So this was the first part of my discussion, where we had the discussion on the emergence of additive manufacturing. We went ahead with three basic process: FDM, SLA, and SLS, and their variants. We discussed about the trends of 3D printers, and about the case studies, and about the specifications of a 3D printer. And I have shown some of the software interface module being used on our lab machine, and also some of the components being printed. So the second part of my discussion will be on sustainable manufacturing. Before I proceed, organizers, are there any queries in the chat box being posted till now? Organizers? So the next part of my discussion is about sustainable manufacturing. As we all know, the sustainable way of designing and developing products had been gaining much importance. Also, it is referred equal by the term like green manufacturing, environmentally friendlier manufacturing, and so environmentally benign manufacturing. Like different terms are there. The ultimate focus of sustainable manufacturing is to design and manufacture products with very good quality and also with improved functionality using energy efficient and the appropriate and relevant technologies. That way we have an objective of utilizing resources optimally and minimizing the waste and emissions and maximizing different R's we call here, like reduce, reuse, recyclable, recovery, reverse design, reverse manufacturing. Like this, we have different R's as a part incorporated with the focus for the economical benefits and also the societal benefits, and the environmental aspect is also very, very essential. And that's the key focus of this FDP, where these technologies have been designed to facilitate environmental sustainability. In environmental sustainability, we have the focus of optimal resource utilization, incorporated with the different R's like reverse design, reverse manufacturing, minimizing the waste, emissions, and so on. These are all some of the significant aspects of environmental sustainability. So in sustainable manufacturing, we have different approaches and different methods. And maybe I'll be focusing on one such approach for discussion. It's called life cycle assessment. So this life cycle assessment is an approach. So for determining the environmental impacts, we'll be following an approach called SKCET approach, the Society of Toxicology and Chemistry, which will help us to understand the environmental impact of a product from the materials phase through manufacturing, use, and disposal. And there are two important standards we refer for life cycle assessment. 14040 for principles and framework, and 14044 for requirements and guidelines. We'll be referring these standards. And we do have different life cycle assessment indicators. Any LCA module is having the capability to find about 16 environmental impacts. But some of the core important impacts from product design, manufacturing perspective is nothing but the carbon footprint, the CO2 based impacts, and we have the kind of acidification, like which accounts for nitrous or sulfur emissions, and eutrophication, which has a PO4 based emissions, or maybe like energy based impacts, results, inferences. As I told, reverse design, reverse manufacture, and so on. It's about the 3 R's and 6 R's concept, but it is very part of sustainable manufacturing. And from energy viewpoint, we need to do an kind of a process-based modeling, where in a traditional perspective, we have two important parameters like a set of inputs and the output. The relationship between the inputs and output is very, very essential from a two-dimensional perspective, but here we are taking a three-dimensional perspective where we need to correlate the inputs, outputs, and the impacts as well as a part of it. This three-dimensional modeling is also very, very essential as a part of sustainable manufacturing. So with regard to additive manufacturing systems, also we do this kind of a three-dimensional process model. And these are the important environmental parameters, impact parameters we consider, like carbon footprint, which accounts for the global warming potential, the CO2. Next, let us spend some time towards this discussing the sustainable initiatives with regard to additive manufacturing. If you see in additive manufacturing, the energy consumption and material consumption, they are the main contributors for the resource consumption. And it includes primary materials, the actual materials for fabrication, maybe like the filaments of polymers, metal powders, and so on, or maybe like secondary materials like support structures as well as some auxiliary materials. Okay, the material utilization has to be optimal, and even the support structures have to be utilized very optimally. And if you see the kind of waste occurring with additive manufacturing systems, they are relatively less when compared with the subtractive approaches. But if you see in the maybe in the case of an FDM process where we use the support structures, now initiatives are being taken to minimize waste as a part of it. And also we can focus on initiatives like where we can go for optimal printing part, or maybe like the support structures reduction with regard to FDM and other equivalent process as well. So the sustainable additive manufacturing is gaining much importance, and we could see in life cycle assessment, as I have mentioned, the initial part is about process-based life cycle assessment. So now I'm be focusing on product-based life cycle assessment, wherein we can try to find the environmental impacts during design phase itself. So we have modules for product-based LCA, wherein we can try to find out the environmental impacts across the phases like materials, manufacturing, use, and end of life. For these 4 parameters like carbon footprint, eutrophication, acidification, and energy consumption as well. And also, we can find across the life cycle phases, we can compare 2 different designs. Say they are made of same material. If you want to compare for 2 different processes, I can give. Or maybe like they are made of same process for 2 different designs, I can find the environmental impacts. That's a part of it. And I will be able to compare the environmental impacts. The next one is which category of impact is higher and so on as a part of it. We do have different eco-indicator method, additive manufacturing system, with it of a system operating with a subtractive approach. I need to compare. Or maybe like I have 2 different, then I have to go with this kind of life cycle assessment based tool, which is a powerful tool for sustainable manufacturing and specifically for environmental sustainability as well. So this is about the second part of my presentation, where we discussed about the sustainable manufacturing, the insights, and life cycle assessment tools, and so on. And also the insights with regard to sustainable additive manufacturing. It's a very interesting domain and which has a lot of research scope. Fine. Now let us proceed with the third part of my discussion. It's about Industry 4.0. Organizers, are there any queries in the chat box?